Hi guys, okay, so in this video we're going to be referring to the concept of infinity that I referred to in the previous videos. So infinity is basically some large number that we're really not willing to quantify. In other words, what I'm saying is that if we assume that infinity is a number, then n equals infinity, right? And if we assume that this is the largest number ever, then a contradiction results when we start adding 1 at every iteration, right? So what's going to happen is eventually we're going to get another larger number, and this process just keeps going on until we reach a contradiction. So what I'm basically saying is infinity is a number that cannot be quantified as a member of the real set. Right, so keeping that in mind, we're going to try to evaluate some limits that help us use this fact, right? So what do you think the answer to this should be? Limit as x approaches 0 for 1 divided by x. Well, if you try to plot the graph for this, we're going to end up with something like this in both quadrants. And if we try to approach x from the right hand side, we approach this point over here. And as it turns out, the function 1 over x is getting larger and larger as x approaches 0. So if you think about this as 1 divided by 4, we end up with 0.25, but we're moving towards the left, right? So that's going to give us a smaller number each time. And this will keep on going. Actually, we're moving from 1 over 3 to 1 over 4. So the next iteration is going to give us 0.2, and this will keep on getting closer to 0, but never actually equal to 0. Very close to 0, but not equal to it, right? So what we see over here is that f of x is approaching a very large number that we can't quantify. So, and if we look at it from the left hand side, the function 1 over x is approaching a larger negative number. That's the only difference over here. So in essence, what we say in such a situation is that the limit simply does not exist. I can't really say that the limit is infinity at this particular point because we can observe two different infinities occurring over here, which is not something that makes sense at this point, and it won't in the later videos as well. So at this point in time, the only thing we can actually say about this limit is that it does not exist. Another example would be the function x squared plus x divided by x squared. So let's try to evaluate the limit as x approaches 0 for this. Using the concepts we've learned from the previous videos, we know for a fact that we can just divide out x squared, which is in the denominator, right? Because x is never actually equal to 0. It's just getting closer and closer to 0. The concept of arbitrarily close to 0. So basically, we can rewrite this limit as x squared divided by x squared plus x over x squared. And that's simply going to give us limit of 1 plus 1 over x. As you can see, the problem over here is that 1 over x is the function we just talked about like a couple of minutes ago. And as x approaches 0 in this particular case, this limit turns out to be a very large number that we cannot really quantify, right? So what happens is the limit for this part would not exist for this particular case, and adding a 1 to that just adds on to the paradox of the situation. So what I'm basically saying is that if one part of the limit does not exist, then there's no way you can actually evaluate using whatever expression that lies to the left of this term. So for this particular function, the limit does not exist either. Okay, let's try to see if we can find an example in which we can use the concept of infinity to our advantage. For example, let's try and evaluate the limit at infinity for a particular function. And what would infinity, the limit in this particular case, be for a function f of x? Well, basically, for that we need to think of a few examples before even approaching this problem. So if you think about it, limit as x approaches infinity for the function 1 over x has to be thought about, right? So we know that the function 1 over x can be drawn as that. We figured this out in the previous video, as well as this one. So what happens when x approaches infinity? So since we know that infinity is a very large non-quantifiable number, we know that it's going to lie somewhere over here. And as we can see, even if we can not like plot a graph at this point, what we can do, however, is put in values for x. So for the function 1 over x, let's start by plugging in 1. We get 1, and if we start plugging in the value 2, we're going to get 1 over 2, right? So basically we keep on doing this, right, until we have, I don't know, 1 over 1000 or something. So what's happening is we have 1 over here, 0.5 over here, and then we'd have, well, 0.33 here, and basically we're trying to approach something over here, 0.001, and this would go on and on and on, right? What we can see is that this would approach 0. It would never actually equal 0, but if the number is increased, like to, I don't know, 10,000 or even like million or something, right, this would approach 0. So what's basically happening is the limit as x approaches infinity for 1 over x turns out to be 0 for this particular case. Let's try to solve another example. What would the limit as x approaches infinity be for x squared plus 1 divided by x squared minus 1? Well, we know for a fact over here that this would basically give you non-variable answer. So what I'm basically saying is that there has to be a way we can express this in an alternate form so that we can use this concept, the 1 divided by infinity, in a way. I'm not going to write infinity because that's gonna confuse you guys at this point, and I don't want to, because in this function this is clearly wrong, because in the function 1 over x, all you can plug in is a real number value, right? We know that for a fact. We just cannot plug in a number that doesn't exist. It's just a concept. It's a very large number. We could place a number like 1 over 10 power 6, right, or 10 power 9 as well, but we can't place infinity. What we can do over here is think of infinity as a very large number that's going to be in the denominator over here. In this particular case, let's try to apply that concept over here, but we're going to need to change this to a different form. So what would I do in a situation like that? It's pretty simple actually. I'll try to divide the numerator and the denominator by x squared. If I do that, I could rewrite this expression as x squared plus 1 over x squared. That's the numerator, and the denominator is precisely this. And if we try to simplify this, it's simply going to be x squared divided by x squared plus 1 divided by x squared. So that turns out to be, in the numerator, turns out to be 1 plus 1 over x squared, right? And in the denominator, it's 1 minus 1 over x squared. Simple, right? So we expressed it in a different form, or rather, I should say, a form that's similar to 1 over x, a form in which we can utilize the concept of an infinity. So as you can see over here is, we have 1 plus 1 divided by a very large number, right? So if you try to plug in a large number over here and keep on doing that until we reach infinity, which is a very, very large number, right? This term is going to turn out to be 0. It's going to approach 0. And that term is going to approach 0 as well. So what we end up with, finally, as the limit at x approaches infinity, is 1 divided by 1. So that gives me the limit 1. Which is really weird, right? Because for a second we just thought a limit like this wouldn't be able to exist. I was like literally blown away the first time I tried to solve something like this. So I'm pretty sure you guys would be as well. Trying to understand this concept is difficult and it could tend to be confusing, right? But what you guys need to understand is that infinity, I'm saying this again and again because it's a very important fact, that infinity is not a number, right? So whenever we use it in the concept of limits, we are thinking of the value x approaching a number, approaching a large number, approaching 0, getting arbitrarily close to a particular number. It's never equal to that number. That's another fundamental concept that you guys need to know. Arbitrarily close to a number, right? So you need to understand this in order to evaluate limits at infinity. So I would request you guys to not think of infinity as a number and to not evaluate the limit as any limit as infinity, and rather use the term does not exist, because that kind of makes more sense. It intuitively, if you think about it, it gives much more meaning to the whole concept of infinity, of some limit approaching a particular number. When you're trying to approach x, right? When you're trying to make x approach a particular number, what happens to the limit when that happens, right? So in the next video, we're going to start talking about directional limits, which is another very important concept that you guys need to know in an attempt to evaluate any particular limit. See you guys in the next video.